Welcome all to the last section of chapter 16, which deals with the relative motion analysis using rotating axes. I should tell you that I'm going to split this section into two parts. So this is part number 1. So the main objective of this section is to study relative motion using rotating axes. Now, just to remind you, previously we did the relative motion using translating axis. So we said that this is a fixed axis, x and y, and if this is the rigid body and the rigid body is translating, then at one single point, and we call it A, we assume that there is a translating coordinate system. Now in this section, we will see that there are many applications where the local coordinate system right here may rotate, and this is why we need to do this analysis. So here are some applications. So if we consider this situation, then point A, if we consider this point A and we draw a coordinate system at this orientation, if you look at the motion as the disk over here rotate and move to the left side, this link will move up, and so point B will translate and rotate. So this is a very clear example of a situation that if we put the local coordinate system right here and we put the fixed coordinate system here, then the local coordinate system will translate and rotate. This is another example over here. That's another example. So we put the fixed coordinate system maybe here. This is, we call it y, and this is x. And now if you put this coordinate right here, so let's say you call this one x and you call this one y, it's very clear that if you follow the motion, this coordinate system will translate along here, and as this one rotates, it will rotate with it. Similarly, here we have the fixed coordinate system being determined, and if we put a coordinate system at this point, then we will see that it will not only translate as the ball or the sphere here move over the slit, it will also rotate because the whole disk rotates. So let's start by the position. Here we have fixed coordinate system, which is identified by capital X, capital Y, and this coordinate system is right here. And also, if we consider that this is a rigid body, and this rigid body has 2 points, A and B. And what we did, we established a local coordinate system, that's X, that's Y, and of course we identify the local coordinate system by writing X and Y and Z in a small letter, while the fixed frame of reference is in capital X and Y and Z. Clearly we can write down the absolute position vector of A, which is RA, and RB. And also, we will have the relative position vector RB with respect to A. So, we will end up with this equation. The position of point B is equal to the position of point A plus the relative position between point B and A. What is new is that we identify capital omega, which is the angular velocity of the coordinate system, and omega dot, which is the derivative of omega, which is basically alpha, which we call the angular acceleration, but this angular acceleration is for the coordinate system. So to establish the relation for velocity, let's consider this example where we have this fire track, which is translating to the right, so it's moving to the right, and at the same time, this angle theta is increasing. Now, we need to establish our fixed coordinate system. So let's say that this is capital X and this is capital Y. And we will also establish the local coordinate system at point A. So this is a small x and this is small y. Now clearly, the small coordinate system is translating with the track as the track is moving to the right. And at the same time, as theta is increasing, this coordinate system is rotating. And if we want to write down the velocity equation, then we should start with the rate of change in position. So we will have drb over dt is equal to dra over dt plus drb with respect to a divided by dt. Now what we will get from the absolute quantities here, Vb is equal to Va plus the rate of change of the relative position vector with respect to time. Now we know that this component will be affected by the fact that this point on the local axis is translating and rotating. Now I'm not going to go through the derivation. You can go and check it in the textbook. But the final equation that we are going to get is this. We will get VB as a vector is equal to VA plus capital Omega cross RB with respect to A plus VB with respect to A, and this one is measured from the local coordinate system. So let me quickly explain what are those new terms. So we are all familiar with VB. That's basically the position, the velocity measured from the fixed coordinate system to point B, and this is also the velocity of A. But what is new is this term. This omega, the capital Omega, is basically the rotation of the local coordinate system with respect to time. So it's the angular velocity of small x, small y, small z coordinate system. And the position vector RB with respect to A is basically, as we did before, it's the vector which is pointing from A all the way to B. So if I want to draw this, then this is going to be going from A to B. This one is RB with respect to A. What is also new is this term. What is this term? This one represents the velocity of B with respect to A, but this velocity is only measured with respect to the small coordinate system. And if you think about it, since the coordinate system always rotate with the stair, with respect to the small coordinate system, this velocity is actually only translation, because it's point B as it moves with respect to A. So in this slide, I'm just showing you what we did, but I'm trying to illustrate what are the directions of these new components that we are not familiar with. So omega RB with respect to A is basically going to be a component of the velocity acting in this direction, while the velocity of B with respect to A measured with respect to X, Y, and Z is the velocity acting in this direction. As I said, this velocity is simply translation because point B can also translate with respect to the local coordinate system. Now, for the acceleration, we need to take the time derivative of the velocity equation. So let me remind you that the velocity VB is equal to velocity VA plus omega cross R B with respect to A plus V B with respect to A, X, Y, and Z. So if we take the time derivative, we will have dVB over dt, which is equal to dVA over dt plus d omega over dt cross R B with respect to A plus omega cross dr B with respect to A over dt plus dVP with respect to A measured from small x, y, and z over dt. Now, the absolute term, we will just get them right away. That's the acceleration of B, which is equal to the acceleration of A, plus the time derivative of omega is going to be omega dot cross R P with respect to A plus omega as a vector cross dr B with respect to A over dt plus the derivative of VB with respect to A measured from X, Y, and Z coordinate system. Now, what we need to focus on here is this. This is the relative position vector, the change in the position with respect to time between point A and B, which is going to be affected by the translation and rotation. And this one is the velocity of B with respect to A measured in the small coordinate system with respect to time. So let's see what are those terms. So I'm not going to discuss the derivation here, but I'm going to write down the equation and then we will discuss it. So we have AB is equal to AA plus capital omega dot cross RB with respect to A plus omega cross omega cross RB with respect to A plus 2 omega cross VB with respect to A measured from the local coordinate system small x, small y, small z plus A, sorry I forgot, this is a vector. So again we have the acceleration AB with respect to A measured from the local coordinate system small x, small y, small z. So let's go over these terms. We have the first term, which is the acceleration of point B. So this is the acceleration of B measured from the capital frame of reference, which is the fixed frame of reference, capital X, capital Y, capital Z. Similarly, the AA is the acceleration of A measured from the fixed frame of reference. So sorry here for the typo, but this has to be capital X, capital Y, and capital Z. The relative terms, which are the acceleration of B with respect to A measured from the local coordinate system, small x, y, and z, and the velocity of B with respect to A measured from the small coordinate system, which is the local x, y, and z, are basically the acceleration and velocity of B with respect to A as measured by an observer attached to the rotating small x, y, and z reference. Now, also we have omega capital dot and capital omega. So those are the angular acceleration and angular velocity of the local coordinate system. So it's the rotation of the local coordinate system as measured from the capital frame of reference, which is the fixed frame of reference. And finally, we have the position of B with respect to A represented by RB with respect to A. There is a component of acceleration in the previous equation that we just showed, which is known as the Coriolis acceleration. And this part is coming because of the fact that there is a point which is moving on a path and the path is rotating. So the idea here is that there is an extra component of the acceleration due to coupling between the motion of the point and the path itself as the path rotates. This component, if you go check it from the previous equation, I'm going to write it down here for you, is 2 capital gamma cross VB with respect to A as measured from the local coordinate system, small x, small y, and small z. This component is known by Coriolis, who's a French engineer who was the first to measure it. So let's reconsider the example that we used to illustrate the velocity of a point which is part of a translating and rotating coordinate system. And just to remind you, we have here the fixed frame of reference, capital X, capital Y, and we have the local frame of reference, small x and y, attached to the bar here, AB, or the link. And we have the collar, which is translating, so the collar might be here, but as this one rotates, it moves downward, so it translates. So in the next slide, I'm going to show you the components of the acceleration and their direction. Now, this is the relative acceleration equation. The acceleration of point A, which is the collar, is equal to the acceleration of point A, which is definitely 0, and then plus the acceleration term, which is marked in pink here. Now, this acceleration term has capital omega dot, which is like alpha, cross RB. So indeed, this is like alpha R. Alpha R is the tangential acceleration. And considering that the arm over here, or the link AB, is rotating, so at this instant, the path is probably going here, and this component of acceleration is tangent to it. Now, the second part is marked in red, and this has 2 capital omegas, which is like the small omega, and R. So this is actually similar to omega square R, which is the normal acceleration. And it is shown here that this part of the acceleration is represented by an arrow pointing from point B to the point A, because point A is like the center of the rotation. And then we have the Coriolis acceleration marked in purple. The Coriolis acceleration is actually going to act in the similar way as the tangential acceleration. And finally, we have the acceleration of B with respect to A as measured from the local coordinate system. And as we explained before, the collar with respect to the small coordinate system is just translating. And this is why its acceleration is always pointing toward the x direction, the small x direction. So to summarize, we have established the relation for relative motion using rotating axes. We started with the position vector, and then we took its time derivative to get the velocity relation. In this equation, we get a new term which is called capital omega, which is basically the angular velocity of the local coordinate system. And also we got a new term VB with respect to A as measured from X, Y, and Z local coordinate system. When we took the time derivative of this equation, we get this long relation between A, the acceleration of A and B, and this new relation we got capital omega dot, which is like alpha, and also we get a new acceleration term which is A, B with respect to A as measured from the local coordinate system. Also, we get a term which is called the Coriolis acceleration, and it is 2 capital omega cross V, the velocity of B with respect to A as measured from the local coordinate system. Thank you. We will now have the second part, which is going to have only one solved problem.